This is a recording from Reunions Weekend 2010 at the University of Virginia, made possible by the Office of Engagement's Alumni Education Program. There is an increase in the amount of greenhouse gases that are facilitating unprecedented changes in the Arctic through rising temperatures, loss of ice cover, ocean acidification, and the destruction of coastal regions. At a seminar on June 5, 2010, environmental scientists Howie Epstein and Stephen Macko, professors in the Department of Environmental Sciences, discussed impacts and the relationship to expected global changes. The session begins with Dr. Epstein.
Thank you very much. The title of our joint presentation today is Climate Change in the Arctic, Bellwether for the Future of the Planet. We're going to take the one if by land, two if by sea approach, and I'm going to talk about the effects of climate change in the Arctic on land. Professor Macko is going to talk about impacts on oceans and seas. We are going to, there will be a little bit of overlap, but I would say most of the material is different, but you may see a few similar things. We will talk a little bit about climate change in general, and then also climate change that's specific to the Arctic. And our plan is to each speak for about a half an hour and have some time at the end for questions and discussion. Okay, so as I mentioned, my section of the talk will be about what's going on land. But I mean, it's really tough to separate, land from ocean in the Arctic. It's really an ocean-driven system. Many of you maybe not be so familiar with the Arctic and Arctic tundra, and not everyone has ever taken a look at the Earth from the top of the North Pole. So this is looking down on the North Pole. This is a view from the top, the Arctic tundra biome. All the areas here in these colors here, everything with the exception of this tannish color here, that's the Arctic tundra biome. Okay, it's a very extensive biome. It's a lot bigger than most people think. What defines the Arctic tundra is the tree line. Okay, the tundra is defined as the absence of trees due to cold conditions at the high latitudes. So all these areas are tundra. They're all, none of them have trees. The tundra is very diverse. There are a lot of different types of tundra. It's not, just because they don't have trees doesn't mean they don't have woody plants. There are a lot of woody plants in the tundra, and actually you'd be surprised, the woody plants almost go to as far north as land goes in the tundra. So again, not being able necessarily to separate land from sea, the tundra is pretty much a maritime biome. Okay, it is. Most of the tundra is located within relatively short distances from the generally ice-covered Arctic Ocean. 61% of the tundra is within 50 kilometers of sea ice. That's the blue buffer. 80% is within 100 kilometers of the ocean and sea ice. That's the blue and the magenta or purplish colors. And so we know that changes in what goes on in the Arctic Ocean and what goes on with the sea ice is very likely to affect what goes on land. They're strongly coupled. Well, I'm going to give you some photos of what the tundra looks like, because a lot of people think that the tundra is a barren wasteland, and actually it's not the case at all. I mean, the tundra can be a very, very lush environment, particularly in the southern tundra. There's a lot of vegetation, and the vegetation pretty much goes until the end of the land in the northern hemisphere. You actually don't find barren landscapes in the northern high latitudes. So I'll just show you some photos of some places, of the vegetation of some places that I've been. Between 2002 and 2006, we worked here along what we call the North American Arctic Transect from northern Alaska through to the Canadian archipelago. If you really want to get into the high Arctic, you actually have to leave Alaska. Alaska's not far north enough to get into the very high Arctic tundra. So you have to leave Alaska in North America and go to the Canadian archipelago. The other place that we've been working for the past few years is this area in Siberia called the Yamal Peninsula. And we have a number of sites along the Yamal Peninsula including last summer we went to the White Island, which is just off the northern coast. So that's what I've been doing for the past decade or so. So the North American Arctic transect, that's tundra, okay? That is the shrub tundra at the very far south edge of the tundra. There are no trees there, plenty of shrubs, lots of green vegetation, very lush. You go a little bit further north, you can lose some of the shrubs. Even further north, it starts to look a little bit more like prairie, but still, there's no bare ground, okay? It's still 100% vegetation cover. And we're not even in the middle of the tundra yet. So here we are, subzone C. What we call subzone C is the middle, the center of the tundra. And, it's starting to look, a little bit more desolate, but still plenty of vegetation. Even further north, the vegetation starts really hugging the ground where the microclimate is a little bit warmer. And then finally, in the furthest north, we get to what we call the polar desert. And you do get, quite a bit of barren, some barren landscapes, particularly if you get up a little bit in topography. The wind is pretty damaging, and you kind of lose the vegetation on the ridge tops, even if it's just a small topographic change. These yellow flowers are poppies. And this was, so you get a lot of vegetation protecting itself in the cracks that form in the soil, and as you go down a drainage, you find some more vegetation because there's more moisture there, and it's a little bit more protected. But this is as far north as you go, and it's still not completely barren. Okay, there's still lots of species here, and also I point out that it's difficult. I'm not sure that we're going to be able to that we can see it, but you have two species of shrubs here. Okay, they're no longer growing vertically, they're growing horizontally. They're hugging the ground where again, the microclimate is relatively warm. You actually have a deciduous shrub and an evergreen shrub. The evergreen shrub is dryas, and the deciduous shrub is a willow, Arctic willow. Okay, so you don't lose woody plants until you almost get to the end of the earth. This is at 79 degrees north latitude. Land in the northern hemisphere, I think, goes to 82 or 83 degrees. This is the Russian transect. This is the forest tundra. Tundra area near forest tundra, going further north. And that's the White Island. You see, you start to have some bare spots, but still plenty of vegetation as you go north. Okay, Professor Macko is going to talk more about climate change in general, so we can wait for him. But these are a lot of the information from this I took from the Arctic Report Card 2009, so it's relatively new information. This is average surface air temperature anomaly, so differences from a mean 1961 to 1990 mean. And you can see increasing from 1900, you can see increasing temperatures. We had a cool period between 1950 and 1970, and then a pretty dramatic increase in temperatures from around 1960 to the present day. You see a lot of interannual variability, but the trend here is clearly an upward one. We're looking at about, in general, close to a 2-degree C increase over the average from 1961 to 1990. That is variable around the Arctic tundra. Some spots will be seeing more warmth than that. Others less warmth, and even a few spots with some cooling. But this is the average for the Arctic. If we look at some modeled results, these are projected surface air temperature changes, and we're looking at the output from 5 different models here. These are global model simulations. So the increase from 2000 to 2100 projected for the Earth as a whole, and these are the projections for the Arctic. Okay, so the Arctic is the region that is projected. Well, it's the region that is experiencing the most warming right now, and it's the region that's projected to experience the most warming in the future. And you can see there's some variability between the models, but they clearly distinguish the Arctic from the rest of the Earth. sea ice. Okay, sea ice is extremely important, and it is probably the aspect of the Arctic that is changing most dramatically, or has changed most dramatically over the past several decades. These are sea ice images from March 2009 and September 2009. So the sea ice is greatest in around mid-March. Mid-March it is at its greatest extent, and it is at a minimum mid-September. Okay, mid-September is the peak of the melt. So this is the winter extent of sea ice for March, and you can see it gets well into the Bering Sea, and it extends down relatively far to the south, and completely covers in the winter, completely covers the Arctic Ocean. In the summer, it recedes. So this is 2009, and this line here is the mean or the median minimum extent for the period 1979 to 2000. So you could see in 2009 there was quite a bit of melt relative to the median value over the past 2 decades. So if you look at sea ice, and I know Professor Macco is going to show some more of this, but if you look at sea ice, if you look at the September sea ice, this is the difference from the anomaly from the 1979 to 2009 period. This is what sea ice has looked like from the late 70s through 2009. Okay, there was a pretty steady decline, and you can see there's interannual variability here, but a pretty steady decline. 2005 was a record year, a record minimum. It went slightly up in 2006, and then 2007 caught everyone's attention because there was huge melt in 2007 and just blew away the record for 2005. And 2008, 2009 have been slightly more than 2007, but still these are the 3 lowest years on record. The reason we had the record goes back to the late 70s. This is satellite information. Okay, we're getting this from a satellite, so that's about as far back as the information can go. So you can look at this online, relatively real time. I didn't get yesterday's sea ice, but I do have this image from just about a week ago, May 27th, 2010. So here's 2007. This is the 79 to 2000 average. And here's 2010. You can see there was actually a lot of freezing in the winter relative to 2007. Actually approached the average, and then very dramatic melt from about late March through late May. And right now there is less sea ice than there was in 2007, which was the record year. So I'm guessing that 2010 is going to be the new record. I mean, that's probably a reasonable guess at this point. What I think is going on here, the reason you get a lot of freezing and then a heck of a lot of melt, is because there's a transition from old ice to new ice, or multi-year ice to one-year ice. So in the past, we may have had ice that has just hung around for year after year after year. Now we're starting to see a lot of new ice. So as the freezing is occurring, it's mostly ice in areas that have only had ice for a year, and then that ice melts very, very quickly. So we see that if we may have had a cold winter, led to a lot of freezing, but that ice disappears rather rapidly as it warms up. And we can look at ice thickness, and one way of looking at ice thickness is we can do it with satellite information now, but the data only go back to about 2004 for ice thickness from satellite. So this is multi-year ice in the red, and this is first-year ice in the blue. And you can see that the thickness of multi-year ice is declining, or has declined from 2004 to 2008. The thickness of first-year ice is essentially the same. This is the satellite record here. Prior to the satellite record, we were able to get some information from submarines in terms of ice thickness. And I'm not sure exactly how accurate these data are, but the general trend is a decline in ice thickness, and the satellite data confirm the continuing decline of ice thickness. So we're not only losing the extent of ice, but we're also the thickness of the ice is decreasing. And we're talking about huge areas, okay? I mean, we're talking about a difference of millions of square kilometers of ice, okay, that's being lost. What is interesting is that these are model projections of sea ice extent. So if you look back at the record that we've gone from about 8 million square kilometers down to 4 million square kilometers in 2007. But these are model projections here. All of these are model projections. These are the actual numbers. And so the actual decline in sea ice is actually exceeding anything that simulation models have predicted at this point. So 2007 here, 2008, 2009 went up slightly, and 2010 may very well be the new record. Professor Macko is going to talk about sea level rise. When we're dealing with sea level rise, we're not necessarily concerned with the ice that's on the Arctic Ocean. Okay, that is essentially negligible because that ice is already displacing water by mass and by volume, and when that ice melts, it won't lead to any discernible change in sea level. What we need to be concerned about with sea level rise is we need to be concerned about ice on land. Okay, there are two major ice sheets, and those are the Greenland ice sheet and the Antarctic ice sheet. So water that moves from ice onto ice from land into the ocean, that would lead to changes in sea level. This is some information on Greenland, and these are temperature anomalies for Greenland, and the red are temperature increases. So most of Greenland is experiencing some degree of warming, with this southwestern portion of Greenland with no warming and even a little bit of cooling. If you look at the melt data, okay, this is number of melt days, the 2008 melt day anomaly, and you can see that in northern Greenland there is quite a bit more days days in which melting occurs in northern Greenland, and then a few spots here in southern Greenland. But southern Greenland is actually, may be accumulating ice, with some of the edges losing ice. I think if you look at the net effect, if you look at the difference, Greenland is essentially losing ice, and there is water moving from the Greenland ice mass into the seas, but it's somewhat variable, with some areas in Greenland accumulating ice and some areas losing ice. All right, I'm going to talk about the vegetation, because that is what I do. And one of the projects that we've been working on is we've actually been looking at the relationships between sea ice loss, warming, and changes in tundra vegetation. And so what we did was we broke up the Arctic into different basins, and we looked at warming in those basins, we looked at sea ice melt in those basins, and then we looked at the vegetation change in the area that is closest to the oceans. So this is one figure that we have developed. These are the different basins that we looked at. This is the sea ice area. This is the temperature. It's an index called the summer warmth. And this is an index of vegetation greenness. We call it NDVI. It's the normalized difference vegetation index. We can get it from satellite data. And basically, the higher that index, the more green vegetation you have. So we've got, essentially in every one of these basins, there's a reduction in sea ice area up to over 40%. Summer warmth index has increased in all of the areas that we studied, all of the areas around the Arctic. Few areas with only minor increases, some areas with very large increases in summer warmth. And most of these areas are also experiencing an increase in the vegetation. Okay, so the vegetation on land, the tundra vegetation, is actually getting greener. Okay, it's increasing its productivity. Most of the areas are experiencing greening, with a few areas showing a decline in greening. The general trend, though, is that the tundra is getting greener. Okay, the vegetation is responding to warming, possibly increases in carbon dioxide concentration, and the vegetation is producing more. We've done a lot of work with this satellite index of vegetation called the NDVI, which I just mentioned. And if you look at Alaska and Canada, this is from a paper from 2005 in the Proceeding of the National Academy of Sciences. If you look at Alaska and Canada, and you look at the tundra of Alaska and Canada, all of the tundra is essentially experiencing an increase in green vegetation. Okay, the yellows and the reds are either represent positive increase or strong positive increases. It's pretty ubiquitous around the tundra. The forest, on the other hand, and there's still a lot of work to be done here in terms of what the mechanisms are, the forest, on the other hand, is going in the opposite direction. Okay, the forest is actually getting browner. And that's a different talk. But today we're focusing on the tundra, and we're going to look at the greening of the Arctic tundra. So these are some results from a 2009 paper from a colleague of mine showing the maximum greenness in some different areas of the tundra. And the general trend is an upward one, where the tundra is getting greener. We could also look at greenness over the course of a growing season, and we can discern whether the growing season is starting earlier or ending later. In some cases, we do see the growing season starting earlier. Here is data from the decade from the 80s and the 90s. This is the 80s, this is the 90s, and we see an earlier start of the growing season and more green vegetation at the peak of the growing season. So there's quite a bit of evidence for this changing tundra vegetation with more vegetation growing there. One of the main culprits, we think, is shrubs. Okay, we think that tundra shrubs are expanding in their range and increasing their productivity. This is a pretty nice study that was done some time ago, close to a decade ago. This group of researchers found a series of photos that were aerial photos that were taken around 1950, and they went back to all those sites. I think there were about 250 photos that were taken during that time period, and they went back and they rephotographed the sites from the same position, and they were able to find changes in shrub extent in a lot of the areas that they went to. In fact, of about 250 photo pairs, they found no areas where shrubs had declined, where the shrubs were actually receding. They found a relatively high percentage of areas where the shrubs were increasing, some areas where there was no change. It's a little bit misleading because you're going from a black and white photo to a color photo, so it looks, of course it looks like the vegetation is increasing. But if you look at certain spots here, you can see that the shrubs have filled in this area of the river here. On this slope, you can see the shrubs filling in here. You can see here where the shrubs have filled in. Okay, so there's a lot of infill and expansion of tundra shrubs. One of the things that my graduate student is working on is he's looking at some old satellite imagery for Siberia. This was a mission called the Corona mission that we flew in the 1960s over Russia. So if you want good imagery of Russia, we've got it. And I'm guessing that they have some good imagery of the United States as well. So this information was declassified probably at least 15 years ago. And not many people have picked up on using it. There have been some groups that have picked up on using it. But my graduate student went and just combed the archives of the Corona imagery for sites at the forest tundra zone in Siberia. And the imagery is pretty well cataloged, and it varies in quality. Some of it's good, some of it's very poor, some of it is cloud covered, and you can't use it for what we're doing. But if you look through enough, you can find some good quality, cloud-free imagery that you can use. So he found on the order of about 15 sites that he found some good imagery for, and he can pair that with high-resolution satellite imagery from today and see what's going on. Now, this was very high-resolution stuff. Okay, this was imagery. Well, the resolution was like a meter or less. I mean, you can see individual trees. So, I mean, he's very good at this. So he would be able to pick out individual trees. I'm not necessarily as well trained, but one of this is a repeat photo imagery from the Kolyma River floodplain in eastern Siberia. This is a 1963 image. This is a 2003 image. This was another mission called the Gambit mission. There was Gambit and Corona at the time, and this is an area that is showing some melting and the appearance of ponds or thermokarst lakes where there were none in 1963. So in 1963, we have a vegetated area here with some polygons on the surface. And in 2003, we see that area has potentially experienced some thermokarst and thawing with some lakes forming here. So you have systems moving in two directions. I mean, you've got shrubs coming in certain areas, and you have vegetation disappearing in certain areas. So here's an area that we actually were able to go to. It's close to one of our field sites. This is near the polar Urals in western Siberia, and this is the Corona imagery from 1968. This is 2005 imagery, and you can see that there are quite a few areas here where there are shrubs expanding here, shrubs are filling in here, shrubs have come in here as well. So, in this area. So there are some really nice imagery where we can see vegetation moving in and then also vegetation disappearing in certain areas. So there's definitely change going on over the past 4 or 5 decades. One of the neat things about this technique is that you don't necessarily see the trees, but you can see their shadows. Because of the low sun angle, the shadows are actually longer than the trees are tall. So it's actually easier to pick up a tree shadow on these images than it is to pick up the actual tree. All right, so what are the implications? I'm getting close to time here. So what are the implications? Okay, so we have potential ice melting. We have reductions in snow cover. We've got shrubs coming in that poke up out of the snow. There are potential changes to the energy budget, the radiation budget of this system. Let's assume we have solar radiation coming in. If that solar radiation comes in and hits snow cover, most of that radiation is going to reflect off. If you happen to have less snow, or if you have a shrub, or in this case a tree, poking up out of the snow, that radiation that comes in goes into heating rather than reflecting, or more of it goes into heating rather than reflecting. Okay, that changes the energy budget. Now I'm talking about land. I mean, we can think of this as an extreme if we talk about the Arctic Ocean. If the sea ice in the Arctic Ocean disappears, that's a huge difference in the radiation budget. Okay, all of that incoming radiation that otherwise would have been reflected back to the atmosphere is now going into heating that water or evaporating that water. So the energy is going to some very, very different things when you change the nature of the land surface. So that's what happens on land when you change from snow to vegetation. So this was a paper published in Science in 2005 showing a couple of feedback mechanisms. If we have atmospheric heating and high latitude warming, we can get earlier snow melt, increasing shrub growth. What that does is it reduces albedo, which is the reflectance of the radiation off the surface. So it reduces reflection of radiation. That increases the net radiation at the surface, which increases atmospheric heating, which increases high latitude warming, which makes earlier snow melt, more shrub growth, and that is a positive feedback for warming. We also have a positive feedback on the ice side of things, where warming decreases sea ice, which decreases albedo, increases net radiation, increases heating, warming. So we have two positive feedbacks here for warming. All right, I should probably wrap it up soon. One more thing I'm going to mention is permafrost, and you're going to talk a little bit about permafrost as well. Permafrost, the whole Arctic tundra biome is underlain by permanently frozen ground. Okay, the whole tundra biome is pretty much continuous permafrost. The top layer of that permafrost will melt every summer, and that ranges from tens of centimeters to a meter or deeper. But only that top layer will melt in the summer. Everything else in the ground remains frozen down to some pretty deep areas. There is some evidence of warming of permafrost. Here are some data from northwestern Siberia of warming permafrost temperatures in a few of the regions. Our information on permafrost temperatures will increase in the future. There's a big project going on called the Thermal State of Permafrost, where they're digging boreholes around the high latitudes, around the tundra region. So our network of information on permafrost and permafrost temperatures is going to increase rapidly in the future. As of now, we have some information that permafrost temperatures are warming. Just briefly, there's a lot of carbon stored in the permafrost. In fact, a recent estimate published in Nature Geosciences found that there's about 40% more carbon stored in the Arctic tundra soils than we had thought in the past. Okay, we've been using some prior estimates that were published in 1982. Recent estimates suggest that those estimates were seriously low. Okay, that there's 40% more carbon in tundra soils than we had thought. 38% of this carbon was found in the permafrost. Okay, so what if some of that, if the top layer of the permafrost melts, so if that melt layer gets just a little bit deeper in the summer, you're exposing organic carbon that had not been exposed in the past. Microorganisms can decompose that, putting more carbon dioxide into the atmosphere. I'm not going to go through this figure, but the bottom line is that the system gets very complex. The system dynamics get really complex. You've got atmospheric CO2 affecting temperatures, affecting the vegetation. The vegetation is working on the carbon dioxide. The sea ice extent is changing, which is changing the temperatures. The permafrost potentially changes, which changes the decomposition dynamics. And these are just a few factors. Okay, I can add boxes, can keep adding boxes to this diagram. And the bottom line is you have a very, very complex system, and we're still in the process of figuring out what is going on. You can also put grazing in the picture. Okay, there's a lot of grazing lands in the tundra. Some of these are native caribou, others are domestic reindeer herds. You can add oil and gas development in the picture. Okay, the area that I'm working in northwestern Siberia, the Yamal Peninsula, that's going to be boomtown for gas production. It already is. Okay, it's probably going to be the most dynamic area of gas production on the planet, providing most of the energy resources for Russia and Northern Europe. So, to conclude, the climate of the Arctic tundra has been warming over the past several decades, leading to changes in sea ice extent, snow, permafrost, vegetation. The tundra's been getting greener over the past several decades. This may be due to increasing shrub abundance. That's something we're looking at. There are very important feedbacks, ocean land surface feedbacks on climate change, and the changes are potentially broad-reaching for humans, other animals, plants, and they do have global implications. Okay, the Arctic system has connections to the rest of the globe, particularly with respect to the ice sheet on Greenland and the Arctic Ocean circulation and global climate. So I'm going to end there and pass it to Professor Macko.
Thank you for coming today. I wasn't, as Dr. Epstein suggested, I wasn't sure who was going to come today. And I've taught oceanography, and I was just kind of curious if any of you, because I've now had like 3,000 students take my oceanography class, and I was wondering if any former students were in the audience. We've had oceanography going now at the university. I've taught it for about 20 years. And over that course of all these students, we've also had teachers that we put on vessels that have gone across the Arctic Ocean on icebreakers. I've actually had a number of students. And my involvement has been more on the ocean side of things. So this talk will not be as green nor as rosy. Part of this talk was actually given to a group of about 100 lawyers in Seward, Alaska, late last year. And at that conference, there were 7 ambassadors to the United Nations. And so this is more of a global talk about ocean sciences and the changes in the Arctic also, but more the ocean side. That's a picture of a vessel called the Bowdoin that is originally out of Bowdoin College up in Maine. It's part of the College of the Atlantic, and a picture taken about 70 years ago by a friend of mine. The Arctic, as you've gotten the feeling from Dr. Epstein, is that the conditions are changing. The rates of change that we see in the Arctic now are unprecedented. There are conditions now that we don't think have existed for about 10,000 years, at least 10,000 years. You saw this, former professor in our department, Michael Mann, has been directly involved with reconstructing the temperatures, and all indications are that the Earth's temperatures are warming. Regardless of how you feel about the implications of human impact on that, the Earth's temperatures are warming. And as the temperatures warm, as you heard from Professor Epstein, the sea levels are going to rise. There's a lot of, concern about where the sea levels are going to rise, especially around centers that have great human involvement, like South Florida, Bangladesh, New Orleans, parts of New Orleans. Not that they're not underwater now, but they will be lost, or the southern peninsula of Louisiana will be lost. What we don't consider often, and part of this co-discussion with Dr. Epstein, is that we are both involved with research in the high Arctic, and a lot of people don't consider the high Arctic and its implications for the rest of the Earth. It has its own unique concerns, but the thing is that the Arctic is changing in a much more dramatic fashion, and that's why we suggested that this was maybe a bellwether for the rest of the planet. It has its own unique concerns. We know that carbon dioxide variations are dramatically rising. How much of that plays in this global warming we could discuss as separate issues, but the fact is that it is rising. There are a number of other greenhouse gases that are rising. These are taken from a couple of different reports, but you can see that the United States and China are the major players in these greenhouse gases. The other greenhouse gas that I don't think you actually mentioned, but methane is a major player in greenhouse gases, and that is increasing annually. And I'm going to show you some data that shows that up in the high Arctic, it's increasing at very, very dramatic fashions. Methane doesn't stay in the atmosphere as long as carbon dioxide, which stays in like hundreds of years. Methane hangs around for 7, 8 years and something, depending. But it has a factor of about 20 times the impact of carbon dioxide on the greenhouse effects. As the greenhouse gases rise, all the models indicate that this will cause this warming effect, and that will warm the seas and melt the ice and cause sea level rise. This, from Michael Mann, projected warming. There are lots of different models. All the models indicate that these effects will be seen in the fairly near future. Within your lifetime, you and your children's lifetime, we will see sea level rise across the Arctic. We will see increasing temperatures. The projections for the Arctic are that the Arctic will change much more dramatically as far as temperatures. Instead of being the 1 to 2 degrees centigrade, the Arctic actually might rise 7 to 10 degrees, depending on the model. The Arctic, as Professor Epstein indicated to you, that it has its own unique set of conditions. There are all these feedbacks. As sea ice melts, there will be changes in the albedo, and there will be increasing temperatures. I will talk about some of the implications of that. This is from a friend of mine up at the University of New Hampshire, Larry Mayer, and he studies sea ice. And what you saw in Professor Epstein's talk is that sea ice reached a minimum in 2007. And that has great implications for some of the less rosy picture that I'm going to talk with you about for the rest of the Arctic. As sea ice melts, there are going to be a number of changes. Some of those changes we would see as being beneficial. There will be a greater access to the mineral resources of the Arctic. One of the largest iron mines in the world exists north of the Arctic Circle. There will be increasing exploration for hydrocarbons. There will be increased tourism. You'll be able to take a boat up across the Arctic instead of riding on the icebreakers like the teachers that I put on the icebreakers. You probably will be on a different type of vessel, maybe escorted by an icebreaker in the not too distant future. So some of those are going to be seen. There will be increasing fisheries. We don't know anything about the number of fish that exist in the Arctic Ocean, but there will be an increase in the number of fisheries that are coming from the Arctic Ocean as the ocean opens up. I mentioned this because about exploration, because just as in the Gulf of Mexico right now, we are unprepared for drilling in deep water, we are totally unprepared for drilling in the high Arctic for oil. There was a small spill in 2006, and it had to do with the Alaskan pipeline, and about 1 million liters of oil spilled. About 1/4 of that was able to be recovered. When oil gets onto ice, we have no way to recover it. There's no way to put a boom across the ice. And so we are totally unprepared for a spill up in the high Arctic. There are indications right now that just some of the early exploration for oil in the high Arctic has increased the level of hydrocarbons in the ocean water already. Just looking for it has increased it. So there aren't getting simple solutions. The presence of hydrocarbons, as you are acutely aware now with the spill in the Gulf of Mexico, will impact fisheries, will in fact impact all kinds of other aspects of the ecosystem. This was a small spill. There could be bigger ones. There are other potential collateral impacts that aren't so obvious that will come from changes in the Arctic. There are materials called gas hydrates. This is a frozen gas that exists in the tundra, in the peats, as well as below the sea floor that will become perhaps unstable, and that methane that's part of those gas hydrates will be released. Remember, methane has an impact factor of about 20 times that of carbon dioxide. There is potential for modification of the trophic structures of the high Arctic, potentially even loss of the diversity. And something that if you don't know about, I'm going to tell you about what's called the alternate or the other carbon problem. And that is by having carbon dioxide increase in the atmosphere, we are increasing the carbon dioxide content of the ocean. And if you recall back to your chemistry, by having carbon dioxide increase in the ocean, we are altering the pH because we form carbonic acid. And by changing the pH, that's lowering the pH from what the ocean is today, we are going to be affecting every organism that lives in the ocean. And we have changed it already. I'll come back to that. So as a statement, with warming, we're going to have warmer ocean waters, we're going to have ice melting, and we're going to have higher stands of sea level. Now, Professor Epstein mentioned the peats, and this is a picture taken from last year on the right-hand side, on the left-hand side, and this was a picture given to me where peats are being lost in sometimes at meters per day. And they have great slumping of the peats coming off. Along with those peats, there is a release of methane that is stored in the peats. That methane is in the form of what these compounds call gas hydrates. Gas hydrates on the lower right-hand side are a structure in which gas is included in a water molecule and great amounts of methane. Some people suggest that the peats themselves might have hundreds of gigatons of methane stored. As those peats warm, that methane will be released. In addition to the methane that's stored below inside the peats, there are other structures, and this is actually not from the Arctic, but this picture right here is actually taken by myself in a submarine off the coast of Louisiana, about 100 miles from where the blowout, the well blowout is happening right now. And that is I would call it a structure, a pillow of gas hydrate. Nobody had ever seen it before, our discovery. And this is what this solid methane looks like. That type of material exists inside of all the sediments of the high Arctic, where the pressure, temperature, stability for gas included in those water molecules exist. There are hundreds of gigatons of gas hydrates that exist in the high Arctic. In fact, there has been some estimates that say worldwide gas hydrates along coastal zones of the continents exist in enough carbon that exceeds all the fossil fuel reservoirs of the Earth. Now, there are some more recent estimates say that maybe it's only half as much, but think about it. All the oil in Saudi Arabia, there's less oil in Saudi Arabia that then exists as these types of structures in the coastal plains of the continents of the Earth. Gas hydrates are unstable. By holding them in your hand, they start to evolve gas, and you can light it. So it's an unstable future energy source, but we have to figure out how to deal with it. Gas hydrates are being broken down today. This is a picture from the Arctic Ocean on the Siberian side, and this is concentrations, the red are concentrations, and the purple are higher concentrations of gas, methane gas, that's coming off of the sediments as they start to warm. And this is another picture just taken recently from off of Svalbard Island, in which the gas bubbles can be seen coming out of the sediments. And there is some suspicion that those gases are now reaching the surface of the ocean, and that means they're filling the atmosphere. 1 degree centigrade temperature rise just around the estimates of gas hydrates around Svalbard Island will increase the amount of gas 20 megatons per year. Okay, and remember, each of those gas molecules has an impact factor of about 20 times that of carbon dioxide. Little suspected, I mean, this is Canada right now is not one of the major suppliers, although because they're smaller population, but the Canadian Arctic and the Canadian shelf, as well as Alaska, could be major producers for methane through the decomposition of gas hydrates. Canadians don't like to hear that. In addition to the changes that we see in the chemistry of the planet as a result of global warming, there'll be changes in productivity. Productivity, when we look at productivity in the world's oceans, we talk about high levels of productivity either in the coastal Arctic, there's lots, or coastal oceans of the continents. The deep oceans are fairly not productive. They're not dead, they're more like deserts. Recognize that when we talk about productivity, we deal with trophic pyramids. We're up here at the top of the pyramid, and we're talking about potential changes in the primary production as a result of global warming and other changes. Primary production may increase in the high Arctic as the ocean opens up, and we might see changes in phytoplankton. These are all called coccolithophores. Those coccolithophores will bloom if there's sufficient nutrients in those ice-free waters. Now, the other side is that on the bottom of all of this sea ice grows an incredible amount of algae. Those are diatoms. Diatoms feed the food chains at the bottom of the ocean on the continental shelf. Without that ice, those food chains are not going to see the same timing of where this algae is sloughing off to feed those food chains. So organisms that depend on the ice algae, which is about 25% by some estimates of the total production of the high Arctic, may no longer exist at the right time. It will still exist because the Arctic will still freeze over, but it will melt sooner, and the food chains that depend on it for particular timing are going to be affected. Arctic food chains are complex. We don't understand them very much. There hasn't been sufficient research on the Arctic marine food chains to really come up with some estimates. We don't know how many fish live under the Arctic ice cap. We can turn to another location that where people have been studying and try to use that as an estimation for the effect on the high Arctic. People have been studying the Southern Ocean. This is the ocean around Antarctica with great intensity, where, in fact, the greatest temperature increases are on the West Antarctic Peninsula over the last 50 years. That same trend of increasing temperature, people have seen that one of the major food resources of the Antarctic, is declining. These are krill. Whales live off of Antarctica, and they consume up to 0.5 ton of krill every day. So all the food chains of the Antarctic, which are dependent on these krill, and here's a whale, and penguins and seals, are going to be affected. That change in trophic structure is being studied in the Antarctic, where we're starting to understand it, but in the high Arctic, we don't understand it at all. The changes in these food webs that are complex in the Antarctic are similarly complex in the high Arctic, in the Arctic Ocean. And as changes influence the structure of the food chains in the Antarctic, it's just like that in the Arctic. We would expect it to be. So that as food materials down at the base of food chains, and this is exactly what's happened already in the Antarctic, that as you change the foods at the base of the food chain, and for example, if we have high krill and low krill population, this is a high krill situation, which phytoplankton feed the krill, and the krill are eaten by seals and penguins and whales and fish, that if you lose the krill, all of a sudden you have to depend on other food resources. They'll still exist. There will be other food resources. Will they be in sufficient amounts to maintain the food chains that we presently have? And the suspicion is in Antarctica, with lower krill, you now have to go through a longer food chain with copepods, amphipods, and eventually going up to the same organisms, so that there is increasing energy loss, not as much numbers, and these higher trophic levels will be impacted and likely be diminished, and maybe actually so adversely diminished that they might go extinct. So as energy flows up through alternative pathways, we have to take that into consideration. As far as the Arctic, we know very little about those food chains. So if food chains change, there might be less productivity, and the higher trophic organisms may be seriously impacted. Fisheries. As the temperatures warm, we have an unknown. We have great unknowns about the effect on populations. For example, here this is fisheries, and right now this is a herring stock in the high Arctic, and the herring stock varies so much annually. We don't know how many fish that will be there once the Arctic Ocean opens up. The stock sizes are so far unknown. How much do these fish actually require the ice cover and the ice algae for their lifestyles? We can turn and there are predictions and pretty good models that we can go to something that you can look at Arctic cod. If you had cod lately, it's probably Arctic cod, because the cod stocks of the North Atlantic are so depleted that they've been closed for decades. But they might be coming from the Arctic. These are the present situations for the Arctic cod. How will loss of ice cover affect them? Well, we know that the Arctic cod won't be where they are today. The water will be warmer. They won't have the ice. They won't have the same nutrition in the food for the lower trophic levels as they have today. Can we turn to some other place where those habitats have changed? Well, in fact, you can. You can go back to the Antarctic, and you can look at this fish. It's the Antarctic silverfish that has a range here, but it requires ice because it lays its eggs in the ice for hatching. In the absence of ice, as ice is receded in the high Arctic, in the high Antarctic, those fish are now threatened. Could this be similar to other fisheries of the high Arctic? We don't know. We don't know that much about it. There will be losses of benthic productivity, losses of habitats for spawning, losses of energy transfer because of the trophic level structure changing. There have been some efforts right now to say, well, maybe we should be worried about this. And in fact, the North Pacific Research Board and North Pacific Fisheries Management Council recently, this was just last year, came out and said, we've got to close fishing in huge sections of the Arctic Ocean. Until we know, we don't want to make a mistake. It was kind of interesting that the same council, the meeting that I was at with these 110 lawyers, there was a representative from Fisheries and Oceans Canada who said, Canada is looking forward to less ice in the Arctic because that will increase the fisheries. Without the knowledge, it sounds dangerous. Higher trophic levels are going to be affected. These are belugas. As we have belugas feeding off of, or other whales or other marine mammals feeding off of the organisms of the lower trophic levels, seals, polar bears are going to be affected. This is not a pretty picture, but it's late in the morning, right? And so here, these organisms are going to be seriously impacted. Loss of sea ice means that the polar bears won't be able to get out to the locations where it's frozen, where the seals are going to be living. Seals are pretty smart. They make their little blowholes up and they hang out, and they can hear the polar bear coming. Well, if there's no way for the polar bear to get there, the seals are going to be, probably the seal population would be temporarily increased at least. But the trophic level will change, the trophic structure will change, and there will be organisms that will be seriously impacted. I'll give you another example of organisms that will be impacted are the birds. I use this, we've done some work on the red knots. And red knots have their flyway across Virginia, and they stay, and while crossing Virginia, they chow down on these eggs of the horseshoe crabs, and they basically double in size as they go across Virginia and Delaware. Well, they go up to the high Arctic on their flyways. Well, as sea level is increasing, some of these flyways are going to be seriously impacted. Those locations which are the breeding grounds for those birds are going to be disappearing. As sea level rises, those coastal terrains are going to be lost. There are hundreds of species, millions of shorebirds that use those coastal zones for breeding, and they are already declining, or they will be seriously in decline as we lose those coastal zones. One other story. The other carbon story is one that as we increase the carbon dioxide in the atmosphere, we are increasing the acidity of the ocean. The ocean is now 0.1 pH units. And I'll call those old synapses out that pH is if you remember, is log of the hydrogen concentration minus the log. So as you have a number that's smaller in pH, that means the acidity of the oceans are increasing. The ocean is presently 0.1 pH units lower than in pre-industrial times. It's been pulling in. The ocean is pulling in this excess carbon dioxide. It's probably pulled in about a third of the carbon dioxide that an industry has added to the atmosphere. The ocean's pHs are now 0.1 units lower, what does that mean? That's about 30% more acid than in pre-industrial times. Some parts of the oceans naturally have changes in pH because of local events, but that declining pH that we see today and the predicted pH as we still continue to have CO2 added to the atmosphere over the next hundreds of years or dozens of years is very predictable about what the pH will be. This is not a model. This is simple physical chemistry. I know maybe physical chemistry wasn't simple, but it is straightforward chemistry, so that the pH of the ocean will reach levels that are lower than we've seen in any record for the past 25 million years. The prediction, the effect is very predictable. The pH of the oceans, pre-industrial times, today, it may be pHs of 7. These look like they're slightly basic in the earth, and the ocean is slightly basic. The pH of the oceans may be 2 to 3 times more acidic within the course of your lifetime and your children's lifetime than it is today because of CO2 emissions to the atmosphere. That's acidification. The organisms that are going to be affected by acid is everything. Organisms that are calcareous, these are those coccolithophores that I showed blooming off of Newfoundland. They have shells made out of calcium carbonate. You put them in slightly acid solutions, and this is what they look like. They're not happy. Organisms that are animals, these are zooplankton, foraminifera. They're made out of calcium carbonate. Their shells will start to dissolve. Organisms like pteropods. This is a pteropod. So you can see these are pteropods. These are their shells slowly being eaten away by small changes in pH. You say, well, not everything is calcium carbonate. Okay, there are organisms, lobsters, crabs, anything that has chitin, skeletons that are exoskeletons, not only the carbonate ones like the oysters too, but these organisms have skeletons made out of chitin. Inside of that chitin is a small amount of calcium carbonate that makes it harder for them. That's when you have the soft crab shells and the hard crab shells, that's the difference, that they have hardening going on because of this calcium carbonate. That will be changed. They won't be able to form their chitin as well. There will be whole ecosystem effects. Every organism in the ocean will be affected. So these are just a list of some of the effects that we might expect to see with acidification. And so acidification is not only Arctic, but it's showing up in the Arctic very much more because it's fresher waters. As the waters are melting, there's forming on the surface, and it's very susceptible to the pH changes. So these will affect pretty much whole ecosystems. There will be huge economic effects. Sarah Cooley and Scott Donnet have done some estimates, and very few people have addressed this issue, but there could be literally billions of dollars in fisheries lost. I'm not as worried about the billions of dollars, but I'm worried that the fact that 1/6 of the world's protein comes from the oceans, and with potential collapse in certain parts of the world's fisheries as a result of lowering pH, that has me have greater concern. This is a time of unprecedented change in the Arctic. What I've shown you probably depressed you, is that there is going to be a time of change that none of it appears to be good. I mean, there is the possibility of mineral exploration. There's a possibility of tourism. There are these, increased traffic across the Arctic because of open seaways. But there are a lot of implications for the change that could not be for good. What it means, though, is that there has to be a time for unprecedented cooperation among all the nations of this planet to reduce carbon dioxide emissions, simply, if it's not for global warming and the effect on the temperatures, simply for things like the increasing acidity of the oceans, the declining pH. Anyway, so that's kind of where I finished. It's the consequences of that change are already here, and they're happening at a greater rate up in the high Arctic than in any other location. And I just lost it. It ended. Anyway, I guess I am ended. Okay, thank you. So we have time for some questions. I'll turn up the lights.
The first question from the audience concerned the possibility that sea ice may be increasing in the Antarctic.
It depends on where you look, okay? And it's just like Dr. Epstein showed Greenland. Well, parts of Greenland, have ice accumulation. And I think there are parts of the Antarctic that are showing ice accumulation, but there are lots of other parts. You have to look at the system globally rather than as an isolated location. And so Antarctica has 5% of the world's water stored, and so it's going to show anomalies that are slightly different from the Arctic. But it's a little bit like the Greenland model, okay? And what's the other curious part about some of these models and sea level rise? Most of them haven't considered Greenland.
So, gentlemen, thank you for your uplifting.
The next question is whether there is more biomass in warm ocean water than in cold water.
Well, I'm not sure that that's true. Our most productive oceans are at the high latitudes. I would say that's probably more true for terrestrial environments, that you have more biomass in the tropics than you do in the Arctics. In the Arctic, you have more dead biomass in the Arctic, stored dead material in the Arctic than you do in the tropics. But some of our most productive marine environments are at the high latitudes because it's not necessarily related to warmth, it's related to nutrients.
I would agree. There are 0.1% of the world's oceans are in what are called upwelling zones. And as those upwelling zones, like off the coast of Peru, when you eat anchovies, that's where they're coming from. And those upwelling zones are going to be impacted as we see that with the anchovy harvests when there's an El Nino event, for example. If you can say that there's going to be warming of a couple of degrees, the impact of that on those upwelling areas aren't well known. For areas like the Arctic or Antarctic, as places warm, I think you're going to see less productivity, perhaps, depending on the nutrient levels. The Antarctic Ocean right now has a limitation, what's called the iron limitation. It doesn't have enough iron to keep everything going. Even with enough nitrogen, there's not enough iron. So there have been a few people who have said, let's sprinkle iron in the ocean and make it have the ocean bloom. Well, with the fertilization, those have been successful in that they can get life more life there? Are we now creating an ocean productivity system that's dependent on iron? Because the kinds of organisms that they're causing to bloom aren't the ones that feed the krill. And so we now, so we're talking about beginning to essentially farm the ocean, and we know nothing about it and the implications. Farming is now a practice that's tens of thousands of years old, and are we going to be able to accomplish this in the 50 years that these events are going to happen? So productivity might increase, I think, on the land, certainly, but the oceans, you might see a diminishment, and that doesn't take into consideration acidification. I think acidification is a great concern. There's a film, it's called A Sea Change, that you might be on the lookout for. It talks about ocean acidification. It was supposed to be on PBS last fall, but I didn't see it. So,
productivity. Clearly in the tundra, that's what we're seeing. The tundra is becoming more productive. But we're not seeing that necessarily for the forests, for the northern forests. That might be going in the opposite direction. So there's definitely variability depending on where you go.
yes.
For non-scientists, listening to two scientists speak, it's you could be listening and saying, this is fascinating. Watching a scientist completely absorbed by the research you're doing, and lots of change going on out there. But as I sit as an audience member, I'm thinking, so what? As a non-scientist, like, okay, it's fascinating. I'm really interested, but as scientists who are watching and tracking these changes, are you in a position, given all the information you're exposed to and the global travel that you're engaged in, to make comments about to what extent is human activity making a serious contribution to the shifts that you're tracking, you're just observing as scientists in terms of CO2 emissions and implications for ocean acidification?
Let me take.
So if I understand your question, well, part of your question is to what extent human activity is causing these changes. Is that correct? Or, yeah. I don't think we have a number in terms of a percentage, but well, I think you have to just step back and go to the bottom line, which are the greenhouse gas concentrations in the atmosphere. Okay, the greenhouse gas concentrations in the atmosphere are of carbon dioxide, methane, nitrous oxide, are all greater than anything that we imagine occurred over the past 700 and something thousand years. Okay, if we look at the past 700,000 years, that we've gone through glacial and interglacial cycles, and during those glacial and interglacial cycles, the greenhouse gases in the atmosphere change. Okay, if you go in a glacial period, the oceans are colder, they hold more carbon dioxide, more of these gases. During the interglacial periods, which we are in one right now, the oceans are warmer and they hold less. Okay, so if we can do different ways of projecting what these, of estimating what these gas concentrations were like in the past. And if we do that, we see a natural cycle that has occurred over this time period that we've been in this glacial interglacial cycling. The concentrations that we have now are outside of that. In some cases, they're extremely outside. Methane is ridiculously high relative to what we imagine it was. Carbon dioxide levels are also higher. Nitrous oxide levels are also higher. We happen to be putting a lot of carbon dioxide into the atmosphere, and methane into the atmosphere, and nitrous oxide into the atmosphere. We know that. So, I mean, I think that's the information that you need to make that decision as to whether, humans are having this effect or not. And it's kind of pretty clear that, well, we're going to see greenhouse gas concentrations way higher than we have now within the next several decades. And there's nothing we can do right now to change that. I mean, we can make some guesses, but we may see 500 parts per million carbon dioxide. It's on a trajectory to be worse than it is now, and anything that we do now will alter the point at which it peaks. But it's moving in that direction. China just recently, in the past few years, overtook the United States in terms of total greenhouse gas emissions. So the United States is, I don't know if we're flat or close, slight increase, but China's like this, okay? So China took over the United States in terms of total greenhouse gas emissions, and that's going to continue. But China's also manufacturing wind turbines at a rate that we're not. So when we move to all, I think a result of this is definitely move toward alternative sources of energy. We're going to have to do that at some point in the future anyway. Now's a good time.
China still has about a quarter of the per person use of energy that the United States has, even though it's now about the same level. Think of the size of the Chinese population. And just to follow up, your question actually has two meanings. One is that, is it human impact? And regardless of whether it's human impact or not, how much of that's human impact, I think, one, we should be worried. We should be worried about houses. We should be worried about fisheries. We should worry about global change. Anything that we can do that might have an impact, we should be doing. And one of those things, so the other is that, is it human? And if we can take ourselves and make ourselves part of that equation, then we can say that, well, even if it's not 50%, if it's 10%, that 10% on a global scale says that we could reduce whatever that level is going to be. That carbon dioxide that's there today is going to be there 100 years from now. We're not going to reduce it. With China going and building a new coal-burning power plant every week, that's going to be increasing. And
so you step out of your science roles and your science hats.
Yes.
And I ask you the inappropriate question, what would you do if you were a policymaker?
This exactly. I got that question from a lawyer in Seward when I gave this talk. Exactly the same question. What could we be doing? And I said, well, as a policy, addressing policymakers, we should be doing everything we can to reduce emissions and looking for alternative energies. And the other thing is we should be dealing with solutions to preparing for these eventualities. We should be preparing for rising sea level. Would I rebuild New Orleans? If a hurricane came by and destroyed Miami, do you rebuild Miami? Knowing that this is the future. Sea level is going to rise. Temperatures of the earth are going to rise. There's a book, it's called Cool It, you might want to look at. And it's by a Danish fellow. And it's all about, well, how do we go about addressing the issues? And I threw out a lot of different issues. And most of those, did you see how many times I said, we don't know very much. We need to find out. We need to start making progress in finding that out. We're close.
Okay, one more question, and then I think we're...
This may be out of your area of expertise, but I don't know anything about the methane hydrates that you were talking about. Are those potential energy sources that we could tap or use?
Exactly. Well, that's, in fact, because they have so much carbon stored that lots of people, the suggestion that I made was that they have more carbon stored than all, or at least half to all or more of all the fossil fuel resources. And people have thought about that. They're explosive. Okay, they're solid gas mixed with water, and then when you heat them up just slightly, and that's what could happen off the continental shelves, and is happening off of the Arctic, that they could be this source of methane that could be tapped into. The other question, though, is that if we're taking methane, if we're taking oil from the Arctic, and we're turning that into energy, we're also turning it into carbon dioxide, increasing the CO2 in the atmosphere. So there is lots of discussion about using those as an alternative energy. But all of a sudden, you're looking at it and say, do we want to?
All right, well, thank you all so much.
Thank you.
There is a
Thank you.